Hello, and thank you for attending this presentation. My name is Amin Dehghani, and I'm a Reservoir Simulation Engineer with Computer Modeling Group. This presentation talks about integrated modeling to assess multiphase flow behavior of CO2 in Wellbore for CCUS projects. Depleted reservoirs, such as depleted gas reservoirs, are very good candidates for CCS projects, but they have their own unique challenges. For instance, the low reservoir pressure means that we have gaseous CO2 at the bottom hole. So when we are injecting CO2 in liquid state at the surface, CO2 will go through a phase transition along the wellbore when going from surface to the bottom hole, as we have low pressure and high temperature at the bottom hole of the CO2 injector. Let's have a look at the overview of what we will talk about today. At the beginning, I will explain the model that was used for CO2 injection modeling, and I'll demonstrate the challenges that we will face. Next, we will analyze a CO2 injector in a standalone form. What it means is that we just analyze the wellbore without coupling to the reservoir to have a better understanding of the pressure profile of CO2 along the wellbore. When we have a better understanding of what happens to CO2 along the wellbore, then we will go back to the model and then provide solution to the challenges that was discussed at the first step. And at the end, we will discuss the temperature profile of CO2 when CO2 is being injected in gas phase. Here we see a schematic of the model that was used. We used a transient thermal reservoir simulator that was coupled to a steady-state well and network modeling tool. CO2 properties were modeled with equation of state. And I should mention that CO2 is being injected here in liquid state, and the injection temperature is 60 degrees Fahrenheit. Here in this plot, we see the wellhead pressure and bottom hole pressure of the CO2 injector. We see that when the CO2 injection pressure reaches to the saturation pressure of CO2 at 60 degrees Fahrenheit, which is around 740 psi, then the well becomes inoperable. And this is shown by these oscillatory behavior at this section. Another interesting observation here is happening at the beginning of this plot. To the beginning of this plot at the very first year of injection, we see that the bottom hole pressure is actually less than the wellhead pressure. And this is not what we normally expect from the injectors. Normally we see that the bottom hole pressure is more than the wellhead pressure. So with this challenge of this oscillatory behavior and this interesting observation of bottom hole pressure being less than the wellhead pressure, let's look at the wellbore in a standalone form and see if we can find a solution and also an explanation for this behavior by having a better understanding of the pressure profile of CO2 injectors. First, let's look at the components of any pressure change along pipelines, as this will help us to better understand the pressure profile of CO2. So the total pressure change of a pipeline includes three main components: the pressure change due to hydrostatic, friction, and acceleration, which we normally can ignore. The acceleration can normally be ignored. On this plot, we see the pressure profile of CO2 at different injection pressures. On the left-hand side plot, the vertical axis is the measured depth and the horizontal one is pressure. And from left to right, we are increasing the injection pressure. Here we see that when we are around the saturation pressure of CO2 at the injection temperature, which is 60 degrees Fahrenheit here, then suddenly a huge gap is happening at the bottom hole, and the bottom hole pressure is increasing suddenly. Another way of looking at this pressure gap is to plot the bottom hole pressure versus the injection pressure at different injection rates. And we see that regardless of the rate, again, at the saturation pressure, we see this huge gap in bottom hole pressure. So this pressure gap is one challenge to overcome when modeling CO2 injection. Let's look at the effect of changing the rate on this pressure gap. Here on the left side, we are injecting at 1, 3, and 7 million cubic feet per day. And we see that as we increase the injection rate, the magnitude of the pressure gap at the bottom hole is also increasing. We can see that here on the right hand side plot as well. So this plot shows the bottom hole pressure on the vertical axis and the gas rate, the injection rate on the horizontal axis. This orange curve is at the injection pressure of 560 psi and the blue one is 570 psi. First, we see that by 10 psi increase in injection pressure, we see this huge gap at the bottom hole pressure. And we see that as we are increasing the injection rate, then the magnitude of this gap is being increased as well. Now let's look at the effect of injection temperature on this pressure gap. Here we see that as we are increasing the injection temperature, then the magnitude of the pressure gap is becoming smaller and smaller. And when we are beyond the critical temperature of CO2, then we don't see this gap anymore. As this is shown by this orange curves at the very end. There is no gap anymore and we see continuous curves here. But before that, we see the pressure gap. And also the pressure gap is becoming smaller and smaller as we are increasing the injection temperature. So another interesting part of this pressure profile of CO2 is happening at the first part. Here, we see that for some of the injection pressures, the trend of the pressure profile looks reversed. For instance, if we look at this blue curve here, we see that the bottom hole pressure is less than the injection pressure at the surface. The injection pressure is here and the bottom hole pressure is less than the injection pressure. Now let's look at the effect of injection rate on this behavior. Here on this plot, we are injecting at the rate of 6 million cubic feet per day. And let's just pick two of the injection pressures, 500 psi and 510 psi. For both injection pressures, we see that the bottom hole pressure is less than the wellhead pressure. Now if we increase the injection rate to 7 million cubic feet per day, first, the blue curve is gone. We don't see the blue curve anymore. And the orange curve, the injection pressure of 510 psi, now shows even less bottom hole pressure. So this means that as we increase the injection rate, the drop in pressure along the well becomes larger. So for some of injection pressure, this results in negative bottom hole pressure or no solution at the bottom hole pressure. So to achieve higher injection rates, we need higher injection pressures. And this requires a suitable tubing inside diameter. So how much bigger tubing sizes are going to help us in terms of achieving higher injection rates? Here in this plot, we see the bottom hole pressure versus gas injection rate at different wellhead pressures. The green curve are 5 inches tubing ID, blue ones are 4, and gray ones are 3. If we just look at the wellhead pressure of 700 psi, we see that by increasing the tubing size, we can significantly increase the maximum injection rate achievable. So by using bigger tubing IDs, we can achieve higher injection rates at the same injection pressure. Now let's pick two pressure profiles. One that is normal, the red one, in which the bottom hole pressure is more than the injection pressure, and the blue one that is reversed. By plotting the components of these pressure profiles, we see that for the reversed trend, the friction component is dominant. So on this plot, on the right hand side, we see the friction, and on the left hand side, we see hydrostatic. So if we compare the magnitude of friction component versus hydrostatic, we see that friction is dominant. So that is why overall the pressure trend is gonna be reversed. Whereas in the normal trend, the hydrostatic component is the dominant component. And that is why as we go further down, the pressure is constantly increasing. Now that we have a better understanding of how the CO2 pressure profile changes, and we know that the pressure gap challenge exists, let's see how we can find a solution to this challenge. The pressure gap itself is due to the discontinuity between CO2 liquid and gas density. And this discontinuity is actually an artifact of the steady state assumption. So one way to overcome this challenge is to use a transient Wellbore simulator. But this is an expensive solution in terms of simulation runtime. There are two other ways to overcome this challenge. First one is to use a lift table, and another one is to add impurity to CO2. Here on the right hand side plot, we see that by use of lift table, which is the blue curve, we've been able to fill this pressure gap. And also if we add impurity, which we've used nitrogen as the impurity here, also again, we can fill this pressure gap. How these approaches are actually helping. When we have pure CO2, we have a saturation line and the phase transition is abrupt. But when we are adding an impurity such as nitrogen, we are creating a two-phase region, and a smooth transition from liquid to gas or gas to liquid is happening, and that is why we don't see the pressure gap anymore. And with the lift table approach, what we do is that in the pressure gap region we are interpolating, and this interpolation is not going to introduce a huge error, as the injection pressure interval that we are interpolating in is very small. We tried these two approaches on the model, and now we see that on the left hand side plot, again we see the wellhead pressure versus and bottom hole pressure, and we see that the pressure gap is now filled and the well is operating along the two-phase region and eventually goes into the one-phase region. And the same case with the lift table. The main difference is that with the use of lift table, the wellhead pressure is almost constant because we're just interpolating in a small interval of wellhead pressures. Whereas in the impurity case, because we are creating a bigger two-phase region, during the two-phase region, the wellhead pressure is increasing. So if we look at the lift table approach, we see four main parts in the life cycle of a CO2 injector. At the very beginning, where the friction component is dominant, the bottom hole pressure is less than the wellhead pressure. And then eventually the hydrostatic component overcomes, but still we are below the saturation pressure. And this is when the wellhead pressure is increasing and also the bottom hole pressure, and the bottom hole pressure is more than the wellhead pressure. Then we enter into the two-phase region, and here, or the pressure gap region, and here we are using a lift table approach to fill this gap. And eventually, when the injection pressure increases enough, now we have liquid CO2 at surface and at the bottom hole because the pressure has increased and we have passed the two-phase region. Now let's look at the temperature profile of CO2. The main parameters determining the temperature profile of CO2 are adiabatic compression, the conductive heat exchange between wellbore and formation, and the heat transfer due to frictional energy loss. When we inject CO2 inside the wellbore, CO2 is being compressed, and this means increase in temperature. And the conductive heat exchange between wellbore and formation is being determined by the value of overall heat transfer coefficient. Here on the right hand side plot, we are injecting at 100 degrees Fahrenheit, which is over the critical temperature of CO2. the dashed line is geothermal gradient, and the injection rate is being increased from left to right. As we increase the injection rate, the adiabatic compression is increasing as well, and this means higher temperatures. Let's look at the effect of injection temperature and the overall heat transfer coefficient. On the left-hand side plot, we are increasing the temperature of CO2 at surface from 90 degrees Fahrenheit to 100 and then 110. By increasing the injection temperature, also the temperature at every depth of the wellbore is increasing, but this only lasts for a certain depth, and eventually overall all cases converge to the same value. And this is happening because when we give enough time for CO2 to exchange heat with the formation, they all are gonna approach the same temperature, and the overall slope is being determined by the geothermal gradient. On the right hand side plot, we are increasing the overall heat transfer coefficient from right to left. The green curve has the highest overall heat transfer coefficient and the blue one has the smallest. So when we have higher heat transfer coefficients, the wellbore is going to exchange more heat with the formation, and it is being pulled more toward the geothermal gradient. In this plot, the effect of tubing roughness and tubing size are shown. On the left-hand side, we are increasing the absolute roughness of the tubing from 0 to 0.006 inches at different wellhead pressures. Let's focus on the wellhead pressure of 700 psi. Here we see that the change in the roughness of the tubing is not going to have a huge effect on the temperature profile. And this effect is even less when we are increasing the injection pressure. So the heat transfer due to frictional energy loss is not playing a major role in determining the temperature profile. Now let's look at the effect of the tubing size. At 700 psi injection pressure, the green curve is 5 inches, red one is 4, and the blue one is 3. So we see that the bigger tubing size is pulled more toward the geothermal gradient. So two phenomena are happening at the same time when we are increasing the tubing ID. So at the bigger tubing IDs, we give more space, more room to CO2 for compression. So CO2 is being compressed less. This means less injection, less increase in temperature. And also when we have bigger tubing ID, this means more surface area for the tubing to exchange heat with the geothermal gradient. So overall, this means that bigger tubing ID is going to show first less temperature and second being pulled more toward the geothermal gradient. In this slide we see the effect of geothermal gradient. So we have shifted the geothermal gradient from the surface temperature of 60 to 80, and we see that at different injection temperatures the overall trend of the temperature also changes according to the geothermal gradient. And this shows that the geothermal gradient, which is determined by overall heat transfer coefficient, is one of the main parameters in terms of how the temperature profile of CO2 is going to be. Now let's summarize what we talked about in this presentation. First, the CO2 behavior inside the wellbore for depleted gas reservoirs was studied in a coupled reservoir wellbore model, as well as a standalone wellbore modeling. And the challenges of this coupling of wellbore to the reservoir were investigated. And we looked at the pressure and temperature profile of CO2 and looked at different parameters affecting these profiles, including the injection pressure, injection temperature, the rate, the tubing size. And also we provided some solutions to overcome these modeling challenges, such as use of lift tables or use of impurities for CO2 injections. Thank you very much for your attention.